All right, so what I want to do is an elementary cellular automata today. There's already an example on P5, by the way. So we actually don't need to write this extensively. And I also talked to our guest lecturer, so we will have a lecture in 30 minutes. So I'm going to keep this session brief. But if you have any questions while I'm doing it, please interrupt and ask your questions, okay? So this is basically the Wolfram CA. It's developed by Stephen Wolfram. It's a basic cellular automata. There's also a link to Nature of Code, and this basically explains in detail and length about how the cellular automata works. But basically, imagine that we have a grid. I mean, this is provided by Daniel Schiffman. I think this explanation with the graphics is phenomenal. So you can follow this. So imagine a grid, and we have simple states, like two states for cells. They're either 1 or 0. So 1 is they're being alive, or 0, they're being dead, okay? And neighborhood means our left and right cell. So if we are looking in the middle cell, we are looking to our previous cell and the next cell in a row, okay? And the generation means basically we are stacking these line by line vertically. And how they are generated is we are looking at triplets. So for the middle cell, we're deciding on its next cell state. And we are looking at its previous and next cell in the same row. So we are looking at this triplet and we are defining its next phase. So imagine that your current cell is dead, like current state is that it's 0, but your left and right are alive. So they're in state of 1. So that is defined, like your next generation is defined by a rule set. So these are basically the cellular automata rules. And these are the triple configurations, right? So it could be 000, 001, 010. So there are 8 possibilities. And for these 8 configurations, you have basically 256 different types of rule sets, okay? And these are determined as rule sets. So for instance, when you have this condition in the generation 010, you're supposed to place 0, so you place 0 here. So the next one is 100, 100 is 1, so the next cell will become 1 basically. So you're moving, looking at every triplet and determining what the next row of cell needs to be. And that gets plotted, right? So we have these sorts of rule sets, and this visualizes basically how the rule set works. So the first rule is when all the cells are alive, next cell becomes dead, so that rule is 0. The first 2 are alive, last one is dead, next one becomes alive, so that's becoming 1 basically. Okay, so there's also an algorithmic component to this. I'm not going to go into further length, but the rules are determined like this. So you give basically an integer 0 or 1 for left and right states and the current state. And these are kind of nested if statements. So we're going to write some of this code, but it's already written actually here. So you can also we can also copy and paste this and kind of explore how it works. So basically, actually, let's do that. So I'm going to just copy this and kind of iterate over it. So this is the current code. What I'm going to do is, so we have 640 pixel wide and 400 pixel height. So let's make this 1200. So let's make it a bit longer so it gets plotted more. So cells means we are creating an array. So the array is defined by width divided by the size of the cell. So the cell width is defined by 10 pixels. So if you have 640 pixel canvas, that means you have an array of 64 cells, right? So there are 64 cells here. And if you want to see them, we can also do like this. So we can do stroke 255. So these are all the cells, right? So the first row, so you saw the animation, so it goes down, right? So the first row is initiated as 0. So here, so when we are in setup, we start this as an array. So it's an empty array with 64 slots, right? So it looks something like this basically. So it's an array like this. So cells equals something like this, 0, 0, 0, 0, 0, dot, dot, 0, ends with 0. So there are 64 dead cells, right? So it's a single line of dead cells. But here on line 17, we are making the middle cell alive. So we are making, we are kind of overriding the state of a middle cell. So that's basically this white cell here that you see, right? And that becomes the seed of generation. So if we don't do this, basically, if I make this 0, then probably we won't get anything. It's all black, because we need some rows to be alive so that the next generations get plotted. And the way this happens is basically we have two variables. So we have a generation and we have a rule set. So the rule set is the Cellular Automata rule set, right? So for every triplet configuration, we are defining its next state. So for me to explain it, it's basically the rule set here is 0, 1, 0, 1, 1, 0, 1, 0, means we basically have that rule set is these numbers here. And these top cell states, these, so I'm drawing a line. So above it, these configurations are all the possibilities. So there are 8 different possibilities of triplets. And there are 256 possibilities for these rule sets. Why? Because this configuration can either yield to 0 or 1. This configuration can either yield to 0 and 1. And if you like, there are 2 possibilities for 8 different conditions. So 2 to the power of 8 is 256 possibilities, right? And that's basically all the rules of the Cellular Automata. So if you go to Cellular Automata 256 rules, go to images. So these are all the rules, basically all the possibilities. So these are some of the rule sets. Like rule 30 means you have to enter this rule set, and we will plot that rule set. So 0, 0, 0, 1, 1, 1, 1, 0. Let's plot that in. 0, 0, 0, 1, 1, 1, 0. That will basically plot this, something else. Right? So that's essentially what I plotted was, let's go back here. That was rule 30. Let's try another one. Rule 150 is 1, 0, 0, 1, 0, 1, 1, 0. So 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0. That was it. 1, 0, 0, 1, 0, 1, 1, 0. 1, 0, 0, 1, 1, 1, 0, 1, 1, 0. So something like this, right? So this was rule 150. Rule 150. So that gives me something like this, right? So all of them have interesting outputs. So they're all pattern based. But basically what happens is we start with a single alive cell, and then it creates this kind of like branching pattern. And it creates like different types of configurations, and the rules are applied in the subsequent cells. So inside of draw, what we do is we just plot the next cell in the next row, and then we update the cells with this generate function. So if you go to the generate function, this basically we define something called next generation. Array cells.length is basically how many cells we have. Let's say we have 64 cells. We create an empty list of 64 cells for the next generation. And then we go through the cell list. We look at the left, the right, and the middle. So this is basically how we retrieve them from the array. So cells I-1 means if I'm looking at, let's say, if I have a list like this, all divided, right? So I'm looking at, let's say, the index 10th cell. Cells I-1 means I'm looking at the 9th cell. I'm looking at cells, I means 10th cell and then 11th cell. So this becomes my triplet. So left, me, and right. And then I send it to a function called rules. And this rules function basically looks at the configuration of this. So imagine left is alive, me is dead, and right is alive. So that means basically 0, 1, 0, right? Sorry, the other way around, 1, 0, 1. So this function retrieves the rule set for this condition. 0, 1, 0 maybe retrieves 1. So it gives me 1, right? So I write next generation as 1 for this slot. So this cell in the next array becomes alive. And that's basically the engine of how this works. I then override it to the cell array and increment generation. So I do this line by line. So every line is looking at the previous generation and updating the current generation. And then basically it's looking at the previous generation, updating the current generation, and then plotting that current generation, and then going to the next generation, right? So this is done continuously. So inside of draw, I have this terminating function called if generation is less than height divided by width, means if you actually go at the bottom of the canvas, you won't run this anymore, right? So generate gives me the next generation. And we can also decrease the frame rate. Basically, if I do, if I do frame rate to be 4, this will run really slow. So you can see how this works, right? This is how each line is plotted by the previous line. And you will, of course, see patterns. If you get like alive cells singled out like this, then they will start branching out as well with the same way, and they will collide at some point, right? So it's kind of plotting the pattern. So let's reduce, let's actually increment the width, so we will have less cells. So I'm going to basically manipulate some of these variables. You can do this too. And we will look at some interesting examples. So for instance, cells dot length divided by 2. So we are starting in the middle. Let's add a few more. For instance, let's do it like this. If random less than 0.5, let's actually make it less than 0.1. Then we do cells I equals 1. So I'm going to turn it alive at a really low, like 10% chance. Like I'm doing this only for the initial row, the first seed. So we will basically have, I'm going to comment this out so that we will see how this looks. So it just, you can see that we have 1, 2, 3, 4, 5. Maybe the ends are also. If I run it again, you will get different seeds floating out. Let's make this really, really low, like 5% chance of the initial seeds to be alive. Okay, so this is the first array, and I got like 4 seeds to be alive, 4 cells to be alive. And then when I enable this generate, it's going to have 4 seeds generating me the pattern with the same rule. Right, so I get something different. Now let's start with this. So it doesn't have to start from the midpoint. Basically, I can input any type of seed I want. Let's also do stroke 0 here. I'm wondering if we can. This is 5. Oh, it's actually not plotting anything, I guess. So white cells are plotted. Field 200 means black. How do we draw empty dead cells? Every time we are drawing white. How about this? If I do it here. All right. So stroke 0. All right. So that's basically, if I'm inside here, that means the cell is alive, right? So it has a fill value of grayish. We can also make this 255 to be like pure white. And then stroke 0, I'm outlining black, but of course it's overlapping with the white cells. So let's make this like this. These are only the alive cells. I'm not drawing any stroke value for the dead cells. So I drew kind of a black outline for the alive cells. So if you look at here, the draw function, these are the alive cells. These are dead cells. So that's how we visualize individual cell groups. I can also make it like this, for instance. I can just draw a rectangle here, but then I'm not getting anything for the dead cells. I mean, let's do a circle. I times W generation times W over 2. And we could do circle mode. Do we have circle mode? Do we have well, we don't have circle mode, do we? What happened? I times W plus W over 2. And generation plus W over 2. All right. That's much better. So I just had to offset these locations. So it gives me the left top of the rectangles, I think. And that's how it draws. The direct mode is not center. So what you're looking at is, for dead cells, we are plotting circles. For alive cells, we are plotting white rectangles. And we don't have to do this W over 2. We could just do W. What's going on now? I guess, oh, this has to be W over 2, sorry. Yeah, so now they're packed. So dead cells are circles, alive cells are rectangles. And we can also do a white stroke around here, and then inside of draw, well, if we do a background, shall we do a background? Maybe not. Background, we have a background? Oh, I didn't see one, but oh, now this is the when I do a background here, it basically just shows me the current generation, right? This is how it's basically generated. So it's generating every line, and that line is basically going down, but it's not plotting it. So if I move this to the setup, now my canvas background is black and I'm plotting onto the canvas. All right. So this has a lot of like comments on it, provided by Daniel, but you can basically look at this again. So let me clarify. Cells are basically a single row of a list that stores only 0 and 1. 0 means the cell is dead, 1 means it's alive. And the generate function basically generates a new row of cells. So if we have 64 cells, I need the next row to have 64 cells, right? So we first initialize it here. Next gen equals array cell.length. Cell's length is 64. And then I'm looking for every triplet, but look at the for loop. It starts from index 1 and ends at cells.length -1. Why do you think that is? Why is the for loop starting from 1 and ends at cells.length -1? Anyone? So remember, how do we look at the triplets? So we have a row, right? Row of cells. So I'm looking at triplets. Why does it start from 1, the index, and ends at length -1? So cells 0 is the first index, right? So it starts from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a row of 10 cells. 0 is the first cell, 9 is the last cell, right? So if I want to call this, I do cells 0. So, but why do I start from I equals 1? Anybody? So we are starting from 1 because we are looking at triplets, right? So in order to find a triplet, I need to start from this index here. So I need to start from 1, basically. So that I have a left cell, which is 0, and a right cell. And then that triplet ends here at the 8th index, because then I will have my last right cell. And if I basically use 9, we don't have a right cell here, right? So there's nothing here. It's empty. Same thing goes for the first index. So there's no left here. That will crash the program because we don't have I minus 1. So that's kind of the issue. That's why the for loop starts from 1, ends at cells.length minus 1. Okay, we're going to have Tansel Hoca join us in 10 minutes. So let's actually make this a bit more interesting. Let's make this 4. So a lot more cells. Wow, okay. It's actually plotting it really slow. Let's make this 5. Frame rate, I'm going to comment it out. So that's a lot faster. Let's not draw a circle here. See what happens. So we just get the live cells, right? So this is the rule set. I'm also going to do something interesting. For instance, the rule set is fixed. Let's initialize it randomly. Okay, how do we initialize it randomly? So every time I press display, I want a different rule set. How do we do that? So let's call a new function, generate rule set. Okay, so every time I run setup, I want to generate a new rule set. So I can do function gen rule set. So what I'm going to do inside is override this array randomly. So I don't know what generation it's going to do, but I'm going to do something like this. So for let I equal 0, I less than 8, I plus plus. Why am I doing I less than 8? Because I only need 8 integers. And inside of it, let's see if I'm missing something here. Oh, this has to be semicolon. And inside of it, I'm going to do, let's create the rule. Actually, we already initialized the rule set. I can do rule set I equals, let's do random. Shall we do floor, or let's write it in the long version. Okay, if random is smaller than 0.5, then rule set is 0, else rule set is 1. There's of course a shorter way of writing this, but I'm just going to do it like this. So what's going to happen is every time I run my setup, every time I run this function, it's going to generate a different rule set. And I want to also print that rule set. So print rule set so that we will look at it. Okay. So let's run this. What does it say? Gen rule set is not defined. Also, this is kind of lowercase, this is uppercase. You need to make sure that they are written the same way. Well, that's the rule set. So 0, 1, 0, 1, 1, 1, 0, 1. That's my rule set. So I don't know which one that is, but it plotted something like this, which is very interesting, no? So let's run it again. This is what I got. Run it again. So keep in mind, I'm also randomizing the initial seeds. Right, so different cellular automatas plotting. And you can see the rule set is also changing every time. And so are the seeds. You got a grid. They look like tapestry, right? So what? All right. So we added something else on top. Yeah, well, you get certain variations like this. So when you make it random, some cellular automatas don't plot patterns. So look at this one, for instance, like with just 3 seeds, they don't generate anything. Just diagonal lines. These look quite nice. This only like did a few stuff. These kind of, I guess, look the best. They also look like seashell patterns. This is another one. Okay, so I'm going to, we basically added something else on top of the default Cellular Automata, but you can do this on P5 libraries, basically anything. So you can take an example file, you can modify it. You can also add kind of your take on the code, right? So you can learn how this works and then start manipulating it. So all I did was basically override this rule set every time the function is run with this for loop here. And I didn't change much here. I just changed the visualization. We could also give different colors for these strokes. Basically, we could do yellow over black as well, if you want. For instance, let's do yellow. Not the stroke. I want to do it here, sorry. Yeah, you can also change the color if you want. We could also make this, by the way, a bit like a random seed. This is kind of what I do. Random seed 0. So let's fix it. And then I want to give kind of a tone of yellow. These are like slight tones of yellow. And maybe we do, well, we should actually draw maybe a rectangle for the black as well. So technically, I could also do this rectangle here too, and this fill, maybe we could make it kind of a tone of black and no stroke. Well, it's kind of subtle. Yeah, this looks like a tapestry. Yeah, you can see small, well, yellow and maybe green. Shall we do green in the background? RGB, so let's make this 20. Green to be, I mean, we have to look at colors, but let's make it like 200 and then 30. Well, yeah, you can see some patterns are emerging because we are randomizing the colors, but maybe we should take out the stroke or add the stroke here too. Let's see. Yeah, these are kind of like glitchy, yeah, like pixelated almost. So maybe keep the stroke and then stroke here too. Maybe make it also black, or this could be just stroke value could be just general stroke 0. Yeah, and stroke weights, let's make it really, really low. Yeah, something like this. All right, so we added some more stuff on top of the cellular automata. Do you have any questions about this one? All right, I'm going to stop here.